Hello, everybody. It's time to get started with the content for lecture module 7. It's all about Mars. So let's go ahead and jump in and look at some of the basics of Mars and actually take ourselves a little tour of the surface, since we have studied the planet Mars with more spacecraft than any other planet, of course, other than the Earth. So we have lots of wonderful pictures of what the surface of Mars looks like. So without further ado, what should we expect for all of lecture module 7? It's all about Mars. We're going to start here in video 1 with the basics. We're going to look a little bit about its orbit, some similarities it has with Earth, and then we're going to take a tour of the surface, look at lots of pretty pictures of Mars because it's just fascinating. Then in the second video, we're going to do the large-scale global view of Mars. Third video is going to be about the Martian atmosphere. The fourth video, perhaps the most exciting of all of them, we're going to talk about water on Mars, where water still is as water ice, and then where water used to be as liquid water, and how Mars used to be a completely different world in the past, about 4 billion years ago. It was a very habitable world with maybe even a global ocean, but certainly very large-scale lakes and rain, river, a whole water cycle. And we'll end it by looking at the Martian polar caps and talk about the 2 moons of Mars. This first video is all about the basics of Mars. So let's just go ahead and jump right in. We are in the last planet of our terrestrial planet series. We are the 4th planet away from the sun. We are finally at Mars, which is commonly most everybody's favorite planet because we know the most about it outside of the Earth. That's because we have explored it pretty extensively, and we have these amazing videos. So this is Mount Sharp, a picture taken from the Curiosity rover, and yes, that is a picture of Mars. You are looking at a mountain of Mars. It looks a whole lot like Utah to me, but it's really Mars. So the Curiosity rover is driving around Mount Sharp, and this is what it would look like if you were there instead of the Curiosity rover. So just an image from one of its many cameras. I always like to start with our side-by-side view. So how big is Mars compared to the Earth? So here we have the Earth, and here we have Mars. Mars orbits the sun further away. We now have semi-major axis larger than 1 astronomical unit. So it's 1.52 AU, and it's about half the size of Earth. Notice that in this image, you can already see a couple of fascinating things about Mars. You can see this sort of ring of blue. That is due to the Martian atmosphere. It's blue for the same reason that our sky is blue. And you can also see a polar cap on Mars. So now we're going to be talking about things that are very familiar to Earth. We're going to be talking about the Martian atmosphere. We're going to be talking about polar caps. And eventually we'll be talking about water, or at least where water used to be. Let's go through our planetary data basics. Let's set the context. And remember, hopefully by now, here we are with Mars, finishing our terrestrial planets. Hopefully you know how a lot of this is going to go, and you can start gleaning the information before I even say it. Just some basic things to know. You should know the semi-major axis of Mars is about 1.5 astronomical units. You should know it's the 4th planet away from the sun. How big is it from center to surface? Its radius is 3,390 kilometers. Scaling that to Earth, that's 52% the size of Earth, or we could say that the radius of Mars is 0.52 Earth radii. So it's a pretty small baked potato. It's only half the size of Earth. We can really see that when we look at the mass. So the official mass is 6.4 times 10 to the 23rd kilograms. Yep, big number, right? Let's put that in context by comparing it to Earth. It's 11% the mass of the Earth, or 0.11 Earth masses. So yes, this is a small baked potato. If we go through our global magnetic field, does it pass the checklist to generate a magnetic field via a planetary dynamo? This is one small baked potato. Do not expect it to have a magnetic field. And if you look down here at the bottom, no, we do not detect a global magnetic field. Is the planet differentiated though? Let's do our comparison. We have not only Martian meteorites, but we have had things that have investigated the rocks of Mars by actually driving around and having pretty sophisticated laboratories on board. So we know the surface rocks have the density of rocks, about 2,500 to about 3,000 kilograms per cubic meter. Let's compare that to the average density of Mars, 3,900 kilograms per cubic meter, a significant drop from the other terrestrial planets, but still larger than the surface rocks, which tells us there has to be something that's more dense in the interior regions, higher than the average density, telling us that Mars is differentiated with a core, mantle, and crust. However, the overall lower density tells us that Mars, forming further away from the sun, uh, formed with different materials, different ratio of materials and different kinds of materials. It is less dense. It probably has a smaller core than the other terrestrial planets, something that we will look at. Let's look at some of the orbital stuff. So what is this orbital period? How long does it take for it to go around the sun exactly one time? So it's 687 days, or if you want a p squared equals a cubed, Kepler's third law, you get 1.88 years. Something a little bit more fascinating is Mars's rotational period. It's 24 hours and 37 minutes. Sounds kind of familiar, right? Very Earth-like at 24.62 hours. Does Mars have an atmosphere? Yes. Does Mars have a magnetic field? I already said that it doesn't. And now we get to talk about the other terrestrial planet with moons. Does Mars have natural satellites? Does it have moons? Yes, Mars has 2. It has one more moon than we do, but both the moons are very, very small and fundamentally different than our moon. Let's go ahead and take a look at some of the interesting things about Mars orbit and start talking about one of the more important points in an orbit if we're designing spacecraft mission. And right now there's a lot of talk about humans going to Mars. So we need to define what opposition is, and then we need to start considering how often opposition comes around. So if you remember back from the beginning of Unit 3, Part 1, where we looked at inferior and superior orbits, opposition is where you have the sun, then you have the Earth, and then on the opposite side of the Earth from the sun, you have the planet. So here would be Mars, opposition. So you have Mars, Earth, and the sun all in a straight line, and Mars is as physically close to the Earth as it can get. This is also when Mars would be going into retrograde. So Mars has a somewhat high eccentricity for a planet, an eccentricity of 0.094, almost 0.1, which means that it varies significantly in its perihelion and aphelion points, which means that if we have opposition near perihelion, then opposition occurs much closer. Mars is much closer to that opposition, an opposition with Mars at perihelion of 0.37 AU. But if we have Mars at opposition at aphelion, then Mars can be as far as 0.67 AU during opposition, which is kind of interesting to think about. We look for oppositions near perihelion, become wonderful times to study Mars. As you can see, it actually is easier to see. These are all images with the same telescope. So this is all with Hubble. And it's whenever Mars is at opposition at aphelion versus, say, Mars at opposition at perihelion. So now let's talk about why we care about opposition and why we might want to know how long it takes for Mars to go from one opposition to the next time it's at opposition. So how long does it take for this geometry of Mars, Earth, Sun, all in a straight line? How long does it take with the Earth going around at its rate and Mars going around at its rate for all of them to line back up in that same geometry? We call the time period from opposition to opposition, or if you wanted to measure it conjunction to conjunction, that would work too. But the time period from one opposition to the next opposition, from one particular alignment of the planets to the next, to the exact same alignment, we call that the synodic period. This sounds familiar because we talked about the synodic period of the moon. That was from full moon to full moon or new moon to new moon. Whenever the moon, Earth, and sun all had the same geometry, they're all in a straight line. So the synodic period is getting the same orbital arrangement, the same alignment between the planets. So for Mars, the synodic period is about 780.3 days, just over 2 years. So the synodic period, the time period between oppositions, is just over 2 years. Why might we care about this? Well, let's think about when we want to send a spacecraft from Earth to Mars. If Mars is way over here, we don't want to launch here, because then the travel distance is much, 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 much greater. We want to launch whenever Earth is approaching Mars at opposition, so we have a short travel distance to the shortest possible travel distance. which means, in a practical sense, if we're going to plan a mission to Mars, we need to wait for a Mars opposition, and then we can send a spacecraft. If we want to have that mission come back to the Earth afterwards, say we put astronauts on it, you have to go there, it gets there at opposition, then you have to wait 2 years for it to be back at opposition so you can send things home again. So this is a very, very important thing as we move into humans exploring Mars, is sending humans there. It's also very important because if you miss this window, so we have a couple of missions going to Mars soon. If you miss the launch window, you are delayed a full 2 years. If you miss launching near opposition, because due to weather, the materials aren't ready, somebody dropped the ball, something like that, then you are talking about a 2-year delay, which you got to keep all those people employed. That is a lot of extra cost. So let's talk a little bit about some very Earth-like properties of Mars, the rotational period and the axial tilt. So the rotational period, one thing we haven't really talked about is how we measure the rotational period. I've casually mentioned a few times in class, but it's pretty easy for something like Mars. People have been able to do this ever since we've had enough resolution to see features on Mars. Because all you have to do is say, hey, look at that feature on Mars. Wait until it's back to the same position again. Watch it as the entire thing rotates around and brings that feature right back to the same place. Time how long that is, and you've measured the rotational period of Mars. So we've known for quite a while, 1 360-degree rotation, a sidereal day on Mars is 24.62 hours. That's 24 hours and 37 minutes. Now, again, Mars rotates in the same direction that it orbits, which is counterclockwise if you're looking down on the North Pole. So the Mars solar day is a little bit longer. And we actually have an official name for the Mars solar day, the noon to noon time. We call the Mars solar day a sol instead of a day. So 1 day on Mars, you don't talk about Martian days, you talk about Martian sols. And then we actually measure how many sols missions have been, certain missions have been on the planet or orbiting the planet. So we talk about how many sols has the Curiosity rover been there, nearly 2,500 Martian sols. And it's kind of interesting, one aspect that now I guess I have time to mention is that when you have people that work on Mars missions, say the people that work on the Curiosity rover, and they are sending instructions to the rover, updates and things like that, they work here on Earth, but they have to switch their entire schedule to sols because that's when that dictates when they can send messages and when they can actually do their job, because the rover lives on sols, not days. Which all sounds fine. You're only off by about 40 minutes per day. But over time, all of a sudden you're working in the middle of the night. Your day that you work is constantly rotating through our days. So sometimes you're working in the middle of the night, and then sometimes you're working in the early morning, sometimes you're working in the evening. This causes a lot of mental stress and strain. So people aren't really allowed to work more than 6 months at a time working on Martian sol time. Let's talk about the axial tilt of Mars. So the axial tilt of Mars is very similar to Earth. It is currently at 25 degrees. So now we have to consider something interesting. A 25-degree axial tilt, so it has the plane of the solar system, its orbital plane, it's tipped over 25 degrees, which is going to give Mars seasons. So Mars is going to have seasons due to an axial tilt. But Mars also has a high eccentricity of about 0.1, and its perihelion and aphelion distances are significant enough where they too cause seasons. So we have two things that are causing seasons on Mars. We have the axial tilt and its eccentric orbit, where we have a full 0.3 AU difference between perihelion and aphelion distances, which causes its own set of seasons that behave slightly differently. So we have to combine both of those to realize that Mars has some pretty complicated seasons, because you have to have both the axial tilt seasons and the eccentric orbit seasons, and those are going to combine in some interesting ways. To complicate things even worse, Mars lacks a large moon, like the Earth does, which stabilizes our axial tilt. So it's always close to 23.5 degrees. It varies a little bit, but not very much. But without it, gravitational tugs from Jupiter mostly will change the axial tilt of Mars, will change its obliquity, as we say. So the axial tilt over time periods of hundreds of thousands to millions of years can go from 25 degrees down to 10 degrees, then up to 50 or 60 degrees. So that thing is just changing its tilt all the time. And it does it in a non-periodic fashion, which means it's chaotic, which means that you can't really predict how it's going to be changing, and you can't really say it's going to change at this rate, at this steady rate. So this makes Mars's history rather complicated. And there are periods whenever it had a high axial tilt, and there were glaciers and things like that. What does this planet look like from a global view? If you are in orbit around it before you're going to make your awesome descent to the planet and you're going to be the first human to set foot on Mars, what would you see? So here are a variety of views of Mars. So this is from a satellite in orbit around Mars, the Mars Global Surveyor. We're looking at Mars in northern summer. Here's what it looks like with the Hubble Space Telescope. Here you can see it's northern. I can tell it's northern summer. You can see the North Polar ice cap. You can see that the seasonal cap has retreated. You can see the atmosphere. You can see that it has these brighter areas, these darker areas. And here's what it looked like from Earth with a really, really good telescope. You can still see that it has polar caps and color variations. You'll also notice that it has sort of a reddish hue, a brownish red color. Why is Mars the red planet? You've probably heard it called the red planet. It's due to the fact that the rocks on its surface are rusted. They are highly oxidized. They contain a large amount of iron oxide, rusts. And what color is rust? Brownish red. So the surface of Mars is rusted, is the best way to put it, giving it a reddish color. So other things to pay attention in the global views. Yes, we're going to have to talk about the polar ice caps, and they are going to have some complicated seasonal variability. You can see these dark and light patches. They will vary in size and extent seasonally, and it's possibly due to different amounts of content of water and carbon dioxide ice in the subsurface. And we will have to talk about the Martian atmosphere. So I want to end this video, just take a little bit of time. So I'm just going to go through these one at a time so we can get a look at the surface of Mars. This is like a series of the pictures of the day. You don't need to know any of this content. You can just enjoy the views. So Mars has sand dunes. So here we have what's called the Namib dune. And you can see a little bit of the Curiosity rover, and you can see this tall sand dune right here. And then you can see sort of this dusty surface with rocks sticking out. Here's another view where where Curiosity actually looked up and could see the Earth and the moon if you really zoom in. And yes, it could resolve both of them. This is the edge of Mount Sharp. So it has some pretty steep peaks right here. But again, it looks like you're in the western United States. Another one from the foot of Mount Sharp. Just looking out, look at this nice cliff line. As a former rock climber, I'm looking at that and be like, man, I bet that has some good rock climbing there. Get some jagged landscape with these sort of sedimentary rocks right here that then have eroded away due to wind erosion, creating some pretty sharp, jagged edges, which you can really see if you zoom in. See some really, really interesting rock formations. As a photographer, I'd love to be there to take photographs of that. Here's our Kimberley, a Martian lake bed. This was the picture of the day today. There's a Curiosity selfie. Look how it's gotten dusty. It's been there for a while. It's had many sols on Mars. This is from a orbiter. I think this is the Mars Global Surveyor, and it's looking down at Victoria Crater right here. You can see that the edges are eroded. We have to talk about erosion on Mars, and it has sand dunes down at the very bottom center of the crater. Here's the Opportunity rover leaving tire tracks as it rolls over a sandy surface, a dune-like surface. And you can see the tire tracks spreading all the way out into the distance at the horizon. And there's probably a lot of dust going on, making the skies look red in this picture. Yes, we watch Martian sunsets, and you can see the sun setting over there. Notice that the sun looks a little bit smaller because Mars is farther away. All right, so I need to go ahead and end the video right there. I hope you enjoyed those views. I will see you in video